And so our next speaker, Corentin Correia, and he will be talking about isoperimetric profile and the quantitative orbit equivalence of lamplighter-like groups. Yes, please.
Thank you. Good morning, everyone. First of all, I would like to thank the organizer for the invitations. Yeah, it's a great honor to have the opportunity to give a talk in this conference. So I would like to talk about joint work with Vincent Dumoncel. And since he's currently listening to me, I wish him a happy birthday. So it's the first time I talk about our joint work. So Vincent, consider my talk as a gift. So I'm talking about more quantitative comparisons between groups, more precisely lamplighter groups or groups which look like lamplighter. So what is a lamplighter? Is a group with a nice interpretation with the drawing that you can see at the bottom. So I will explain it with more detail later. So we want to see groups as things that act on a probability space. So we really have a measure theoretic viewpoint. So let's consider X mu a standard and atomless probability space. So briefly, standard means that X is a Polish space endowed with the Borel sigma algebra. Keep in mind that in fact they are all isomorphic and representative is just the unit interval with the Lebesgue measure. So these are very nice space. So I see groups as things acting on X mu. First, I say that a group G is acts on X mu and its action is PMP if it acts by bimeasurable bijections, preserving the probability measure mu. So PMP means probability measure preserving. Okay. And I will consider free action, or I should say essentially free, because I see freeness up to zero measure. So for almost every x, when I apply some g on x and I get x, it's because g is the identity element on g. Okay? And such actions, so PMP free actions, always exist for all, let's say, countable groups. Just look at the Bernoulli shift. So you have 0 and to the power of G, and G act on it by shifting the, the indices. Okay? And it's a free PMP G action where the space is endowed with the Lebesgue measure to the power of G. So such actions always exist. And I'm working with amenable groups. What is an amenable groups? It's a group admitting a Fulner sequence. What is a Fulner sequence? It's a sequence Fn of finite subset of G, which is almost invariant with under the action of G on itself by left translation. What does it mean? If I consider little g in capital G, when I look at G times Fn, it's almost Fn. So the cardinality of Gfn minus Fn over the cardinality of Fn tends to 0 as n goes to infinity. So this is very nice. These are very nice groups. They look like Z, in fact, in the dynamical viewpoint. Be I will give more details about this. So examples, finite groups are amenable. Just take Fn to be the whole group. Z to the power of d is amenable. Consider Fn as the cube 0n to the power of d. Also, you have many stability properties. For instance, amenability is stable under direct sum, product, extension, stuff like that. And you can prove that solvable groups are amenable. And a counterexample is, for instance, a free group. So let's compare groups with a measure theoretic viewpoint. So I say that G and H are orbit equivalent if they admit actions, free PMP actions on some X mu. so an action of G and an action of H, which admit the same orbit up to zero measure. So for almost every x in capital X, its orbit, its G orbit is equal to the H orbit. And X mu is called an orbit equivalence coupling between G and H. So the idea is that since we assume that the actions are free, then the orbits pointed at some of its points has the same structure as a Kelly graph of G. Imagine G as a finitely generated group, for instance. You can endow orbits, so pointed at some point, with the structure given by the Kelly graph of G. So maybe if G and H admit free PMP actions having the same orbit, maybe the orbit will capture the structure of G and H. Okay? And this is what we can see for non-amenable groups, because you have many rigidity results in this context. So for instance, Damien Gaborio proved in 2000 that if you take any two fluid groups, and if they are orbit equivalents, then they must have the same number of generators. Okay, but Hansen and Weiss in 1980 proved that any two infinite amenable groups are orbit equivalent. So you only have flexibility in the amenable world. So for instance, a group which is amenable will always be orbit equivalent to the group Z. Okay. So we would like to capture the geometry of amenable groups. So how to strengthen the definition of orbit equivalence to have to get an interesting theory. Let's look at the orbit equality in the definition of orbit equivalence, and let's get a more precise description of this equality. So if so let's pick some little x in X. So its G orbit is equal to its H orbit. This means, first, that if you consider little g in capital G and you apply it on X, you get something in the G orbit, but also in the H orbit. So G acting on X can be written as some element of H acting on X. And this element is denoted by CGH of GX. Okay. And conversely, when you consider little h in H acting on X, this can be written as some element of G acting on X. And this element is denoted by CAG of HX.
May,
So
may
this, yeah,
Sorry for interrupting. May I ask you one question? So you mean the orbits are for almost every x, not so almost they coincide almost everywhere. Yes, not exactly coincide.
the equality is exact.
Exact or
Yeah,
exact, but for almost all
exactly.
x. Yes. So
Exactly.
there may be some orbits which are different, some singular orbits we don't know, and for all others are exactly coincide. Understand. Thank you.
Exactly. So another definition of orbit equivalence is there exists some a subset of full measure which is invariant by the actions and on which on which the orbit are equal. Yeah, exactly. Thank you for your question. So
Thank you.
this is for almost every x, but the equality between the orbits is exact. These elements are so the CGH of GX and CHG of HX are unique by freeness, and they always exist because this equality is exact. And this gives you functions from G times X to H and H times X to G, which are called the cocycles of this orbit equivalence couplings. And in fact, they tell us how much we have to distort the orbits to move from the dynamic of G to the dynamics of H. So when you fix the element on a capital X, you get a bijection from G to H, so for one cocycle. Why bijection? It's because the orbits are equal and the action is free. But X is endowed with a structure of probability space. So in fact, when little x move, you get a random bijection from G to H. Okay, so this is why I talk about measure theoretic viewpoints of groups. So now let's consider that G is generated by some subset SG, usually finite, okay, and H2. Consider some little g in SG, so a generator. Is the cocycle on G a generator of H, or maybe not far from being a generator of H? So this is the first question that we ask before defining quantitative versions of orbit equivalence. So what does it mean to be close to a generator of H? So we can give meaning to this thing. So if H is generated by SH, we can define for every of its elements its length, so the length of little h. This is the minimum number of generators that you need to get h. When you make the product, you get h. So for instance, when h is equal to z with the subset finite generating set, the singleton one, in fact, the norm is exactly the absolute value. Okay. And also, if the subset are finite, the generating subset are finite. In fact, when you change this set, you get asymptotically the same information in terms of the norm. Okay. So let's notice that if an element has a norm 0, this means that this element is the identity element of the group, because the identity element can be written as an empty product of generators. And what are the elements of norm 1? These are exactly the generators or its inverses, but except the identity element. So what does it mean to be close to a generator of H? This means that your norm is small. And so the goal is to study the norm in H of the cocycle from G to H, and the norm of G in G of the cocycle from H to G, but based on generators of G and H. So this is the goal. So let's now define a quantitative version of orbit equivalence. So I consider X mu an orbit equivalence coupling between finitely generated groups, G and H. I consider phi and psi maps from R plus to R plus, and I assume that they are increasing for some reason. And I say that X mu is a phi psi integrable orbit equivalence coupling from G to H if the cocycle from G to H is phi integrable. So this means that this is integrable up to some function phi that you put on the norm of the cocycle from G to H. Okay, so for every G, you need a constant Cg, positive constant, so that the integral of phi of this constant times the norm of Cgh is finite. Okay, Cgh based on G. And if the cocycle from H to G is psi integrable with the similar definition. So we need, in fact, when you consider phi of x equal to x, for instance, this is a definition of integrability, okay? And you don't need this constant Cg and C prime h. If phi of x is x to the p, you get LP conditions, okay? But These constants are useful if you consider, for instance, exponential integrable orbit equivalence. Okay, so this gives you another definition, and you need it for this notion not to depend on the finite generating set that you have, that you consider. If you change, you have a change of constant, so that's why you need it. Also, I will put L0 instead of phi or instead of psi if there is no requirement on the corresponding cocycle. So for instance, when I talk about an orbit equivalence coupling, which is log L0 integrable, this means that the cocycle from G to H is log integrable, and I ask nothing for the other cocycle. And for L0, L1 half, for instance, I ask nothing on the cocycle from G to H, and I want the cocycle from H to G to be square root integrable.
Just
Okay, so
may I ask, so
yeah,
this means, for instance, every orbit equivalent coupling between G and H is L0 integrable. Yes?
exactly. And the
L0.
meaning of that
L0,
is,
L0. Is
yeah,
exactly L0, L0. Mhm.
exactly. So, in fact, so as I said, so Einstein Weiss tell us that we only have flexibility result in the amenable world for orbit equivalence. With this quantitative version, we are able to capture the geometry of groups thanks to a nice invariants which are called isoperimetric profiles. So let's consider G a finitely generated group. Um, let's consider a subset, finite subset A, and the ratio cardinality of A over cardinality of its boundary. What is the boundary? Is the set of points in G outside A, which can be reached from A by using generators. So it's Sj times A minus A. It's its boundary. So let's consider the supremum of these quantities over all the subset A of cardinality less than n. This is, by definition, the isoperimetric profile on the integer n. So, in fact, it's a measurement of amenability because G is amenable if only if its isoperimetric profile is unbounded. To prove it, consider A equal to Fn for a Fellner sequence Fn, as I introduced in the definition of amenability. So I will give examples of isometric profiles later, but keep in mind the philosophy of isoperimetric profile is that the faster the isoperimetric profile tends to infinity, the more the group is amenable. So, before stating the rigidity result on a quantitative orbit equivalence, I just introduced some terminologies. So, given f and g function from R plus to R plus, I say that g dominates f if there exists some constant c such that f of x is less than c times g of c times x. Okay, so it's like a big O of g, but you put a constant inside g. And I say that f and g are asymptotically equivalent if f is dominated by g and also g is dominated by f. Okay. Now let's state the rigidity result found by Delaby, Koivisto, Lemaitre, and Tessera in 2023. So consider phi an increasing map such that t over phi of t is increasing. For instance, phi is LP, for instance, or the logarithm. Okay. If there exists a phi L0 integrable orbit equivalence coupling from G to H, So an orbit equivalence coupling for which the cocycle from G to H is phi integrable. Then you have this obstruction. Phi composed with the isoperimetric profile of H is dominated by the isoperimetric profile of G. So this is an obstruction. So let us illustrate this result with an example with the easiest finite amenable group that we know, the free abelian groups. So we know that the isoperimetric profile of ZD is n to the power of 1 over d, okay? So if there exists an orbit equivalence coupling from zk plus L to zk, which is phi L0 integrable, then phi has to be dominated by x to the power of k over k plus L. For instance, from z squared to z, phi has to be less than the square root. Okay? So it's a quantitative comparison between groups, and here we managed to distinguish groups and to capture their geometry. So this say that the cocycle from zk plus L to zk cannot map generators of the big group zk plus L to generators of the small group zk. Okay, they are mapped to elements which are far from being generators because you don't have enough room. Okay. And in fact, it's sharp because Delaby, Koivisto, Lemaitre, and Tessera build explicit orbit equivalence coupling, which are LP L0 for every p less than this ratio k over k plus L. So we managed to capture the geometry of the groups. So let's sum up their results. What about the existence of an LP L0 integrable orbit equivalence coupling from the big group zk plus L to the small group zk? It's possible for p less than k over k plus L, but it's not possible for p greater than k over k plus L. And briefly, what about the case where p is equal to this threshold? And I proved that this threshold cannot be reached. Okay, so I will not give detail on my theorem, which is more general, but this is a philosophy. We cannot reach this bound. So let's give another application of this theorem of Delaby, Koivisto, Lemaitre, Tessera on lamplighter groups, the groups we are interested in. So first, I need to define Reth products. So Reth products of two groups, lambda and H, is lambda Reth H. This is the semi-direct product of H acting on the direct sum of copies of lambda index on H, where H acts on this group by translating the indices in H. Okay, so some interpretation of these groups. So the direct sum can be seen as a set of maps from H to lambda of finite support. What does it mean? This means that F map every element on the identity element of lambda, or all elements, but finitely many, except finitely many elements. Okay. And this can be seen as colorings of element of H by element of lambda. Okay. And for the group on the left, on the right, sorry, so H, this is some cursor that you put on some element of H. So, and what is a lamplighter? This is exactly when lambda is finite. So you have only finitely many colors that you put on some elements of H. So let's give an example with nice drawings. So for instance, when lambda is the group with two elements and H is equal to Z, So the cursor that you put on every element of Z is just some lamplighter, so some guy who is moving in the integer, okay? And the colorings are saying that at some integer the light is off or the light is on, okay? So off if it's 0, on if it's 1. So these are the two states given by the group lambda Z over 2Z. And this group is finitely generated. You have two generators, well-known generators. The first one is the one in purple. So the coordinate on the left is the function, the zero function. So you do nothing on the lamp, and the coordinate in Z is 1. This means that the lamplighter moves from some k to k plus 1. And the second generator is the following in blue. So the coordinate is on Z is 0. This means that the lamplighter doesn't move. And the first coordinate is the function, which is 0, except on the integer 0, which is mapped to 1. And this means that you change the states of the lamp at the site on which the lamplighter is. So if it's on, you turn it off. If it's off, you turn it on. So these are a very interesting group for geometric group theorists. So let's apply Delaby, Koivisto, Lemaitre-Teixeira theorem. So we know that, so when the base group is Z and lambda is a finite group, lambda ref Z has isoperimetric profile log n. This is due to Herschler in 2003. So by Delaby, Koivisto, Lemaitre-Teixeira, if you have an orbit equivalence coupling from this lamplighter to Z, which is phi L0 integrable, then phi has to be less than log. So this means that the lamplighter is a very big group compared with Z, so this cannot map, the cocycle cannot map generator of the lamplighter to generators of Z. You don't have enough room to do this in a measured way. Okay. And again, this is sharp because it's possible to build log to the p L0 integrable orbit equivalence from the big group to the small group when p is less than 1. So in fact, we managed again to capture the geometry of these amenable groups. So yeah, I didn't mention that this lamplighter is amenable, okay? So because we have existence of log to the p L0 integrable orbit equivalence coupling from these groups to Z when p is less than 1, but the author proves that it's not possible for p greater than 1. And again, what about p equal to 1? And I proved that this is not possible to have such coupling. Okay. So that's it for the state of the art, an overview of no, sorry, I forgot something. So this authors also prove stability results. So from H to K, if you have an orbital equivalence coupling which is phi psi integrable, then the same holds for the lamplighter based on H and the lamplighter based on K. You also have phi psi integrable orbital equivalence coupling. You can produce from such coupling from H to K, you can produce another one from the lamplighter over H and to the lamplighter over K with good integrability conditions. And it's again sharp because we can relate the isoperimetric profile of lamplighters based on H to the one of H. And you can also apply it many times by considering iterated ref products, okay, and you get the same results. So now that's it for the overview of this topic. So let's move on to our joint work with Vincent Dumoncel. So we consider not lamplighter groups, but lamp shuffler groups that I will define. We build orbit equivalence coupling between these groups. We quantify the co-cycle, so we, given some such construction, would know we want to know for which phi and psi these co-cycles are phi integrable and psi integrable, and we want to know if it's optimal. So to know it, we have to compute the isoperimetric profile of these lamp shuffler groups. But first, let us define lamp shufflers. So I recall for the lamplighter the idea that you have colorings of elements of H by element of lambda and colorings of finite support. Okay, and H is a cursor at some H. Here, it's a bit different for lamp shufflers, but it looked like, in its definition, it looked like the definition of a lamplighter. So this direct sum over lambda is replaced by a set fsim of H, which is the set of permutations of H of finite support. Finite support here means that for every H, except finitely many of them, sigma h is equal to h. And this can be seen not as a coloring, but as relabelings of these elements. So h carries the label sigma h. And again, for the group on the right, H is so an element of H can be seen as a cursor at some element of H. Okay, so it's some kind of it's somehow the same geometry, the same intuition. Okay, but it's a bit different.
May,
So
may,
yeah,
sorry, may I ask so here you eliminate lambda, yes, you use only H.
there is no lambda exactly.
And this is like a rest product of H no, not with itself, but like the reduced rest product. Yes, when you consider only maps with finite supports, but you consider only bijections.
Yeah, yeah.
F
Somehow, yes. It's not
somehow
a
this
ref
rest
product.
product. Mhm.
Yeah, yes, it's a bit similar to lamplighter, but it's not a ref product. But
Mhm.
yes,
Yeah, no,
somehow
and
there.
yes, yes. So it can be no. Okay, okay. I understand. Thank you.
Thank you for your questions. So we proved, as Delaby, Koivisto, Lemaitre, and Tessera, a stability result if some finitely generated groups H and K are phi psi integrable, orbit equivalent, then the same holds for the lamp shuffler based on H and the lamp shuffler based on K. They will be phi psi integrably orbit equivalence. And when you iterate this theorem, you get also the result of a lamp shuffler iterated n times on H and on K. Okay. So we established this stability result. What about when you don't have the same number of iterations of the lamp shuffler? So we build an orbit equivalence coupling from the nth iteration of lamp shuffler on zk to zd, and we get this quantification that you can see. So L0 on the right, and on the left, the nth iteration of log to the power of p for every p less than 1 over k. So it's a bit difficult to say it in orally. Just keep in mind that they are in fact optimal because we compute the isoperimetric profile, so to establish that this is optimal. So we compute it because it was not known. We have some results on isoperimetric profile of Lemschufflers. This one is due to Herschler and Zhang in 2023. So Lemschuffler over 3 abelian groups. So for instance here over zk, its isoperimetric profile is log over log log to the power of 1 over k. And this also holds when h has polynomial growth of degree d, okay? But for bigger groups, you don't have sharp estimates. We only have coarse estimates due to Saloff-Coste and Zheng and Herschler and Zheng. For instance, for the nth iteration of Scheffler over zk, its isoperimetric was not known if n is greater or than or equal to 2. It was not known. So we computed it. So the assumption are the following. So let's consider H, so the base group of the Lemschuffler, to be finitely generated, and we assume that it satisfies mild assumptions. For instance, when you put a constant inside its isoperimetric profile, you don't change anything. It's a big O of its isoperimetric profile. So for every example we know the isoperimetric profile satisfies this condition, okay? And you assume that the isoperimetric profile of log over log log is asymptotically equivalent to the isoperimetric profile composed with log. So assume that the isoperimetric profile of h is the logarithm. This works also, okay? Then we managed to relate the isoperimetric profile of the Lemschuffler based on H with the isoperimetric profile of H, because the isoperimetric profile of H composed with the logarithm. As for, in fact, lamplighter over Z, for instance, okay. And by iterating this result, this statement, we get also the isoperimetric profile of the nth iteration of Lemschuffler of H. So we don't have any example of groups which does not satisfy this assumption, except for H having polynomial growth. But as I said, this has been done by Herschler and Deng. Okay. So now that we know the isoperimetric profile of these groups, we can now check that our orbit equivalence couplings we build between Lemschufflers are in fact quantitatively optimal. So the quantification that we found are optimal. So we are very happy. So in the title of my talk, I didn't write, Lemschufflers, but I wrote lamplighter-like groups. So groups which look like lamplighter. Because in fact, we investigated orbit equivalence for halo products. What is a halo products, roughly speaking? So they have been introduced by Anthony Genevois and Romain Tessera as a natural generalization of lamplighters and Lemschufflers. So you have a semi-direct product of H on some groups on which it acts. This groups is like something based on groups on which H acts, okay, and these groups as colorings. So this is this kind of idea. And in fact, they proved many results on the quasi-isometry between these groups. What is quasi-isometry? Is geometric comparisons of these groups, but you compare it coarsely, okay, with some constant, okay. So very roughly speaking. And the starting point of our work with Vincent Dumoncel was these questions. If two groups are not quasi-isometric, sorry, how much their geometries differ, okay? And in fact, quantitative version of orbit equivalence give an answer to this question. This give a more quantitative comparison between these groups. And I'm sure I will make you want to study this group because they have so this Halo product. They have a very fancy names like lamp jugglers, lamp designers, lamp cloners, lamp braiders. For geometric group theorists, they are very interesting in terms of the geometry. So thank you for listening.
Thank you very much. Thank you. Very interesting talk. Let us thank the speaker. Thank you.